Welcome to the deep dive. Today we're jumping straight into agentic AI. We're looking at the paper DeepAgent, a general reasoning agent with scalable toolsets. Honestly, if you're building LLM agents right now, this paper introduces like 4 key architectural ideas you really need to understand.
Absolutely. So the first big insight, DeepAgent basically throws out the old agent loop playbook. It's this end-to-end reasoning agent, right? It pulls together thinking, finding tools on the fly, and actually doing things into one smooth process. No more of those stiff, step-by-step workflows like React.
Okay, and the second major shift deals with something that plagues these long-running tasks, the context window just exploding.
Precisely. They've built in this autonomous memory folding idea. The agent itself figures out when it needs to, like pause, take a breath, and compress its whole interaction history. It squishes it down into structured memory, episodic, working, and tool memory. It saves a ton of tokens, but keeps the important stuff.
Right, okay. And then number 3, the training. Training these agents with RL, it's notoriously hard, isn't it?
Definitely. So they call their method ToolPO. It's a novel RL approach. What's clever is it uses LLM-simulated APIs. Think of it like a safe sandbox. This makes training stable and way more efficient than trying to hit real flaky APIs constantly. And crucially, it uses this really fine-grained credit assignment. It rewards good intermediate steps, like picking the right tool, even if the whole task doesn't succeed in the end.
And the results, what did all this add up to?
Well, DeepAgent pretty much consistently beat the baselines across, I think it was 8 different benchmarks. It really shone, though, in situations where it had to find the right tool from a huge open set. Think Toolbench, that's the big one, right? Over 16,000 APIs. That's where this unified approach really pays off.
Okay, let's unpack the why behind this. For the engineers listening, the ones actually building these things day to day, what were the biggest headaches with older agents that DeepAgent tries to fix?
Yeah, the core problem was really about generalization. The traditional models, your Reacts, your plan and solve types, they were stuck in those rigid reason, act, observe loops. They worked okay for simple things, sure, but hit 3 big walls when things got complex.
Yeah. Okay, what were they?
Well, first, a lack of real autonomy in how they executed steps. Second, they just couldn't dynamically look for new tools while running if they needed something not preloaded. Tough luck. And third, managing memory over long interactions. Pretty poor, honestly.
So if you asked it to plan a complex trip and it needed, say, a very specific airlines API that wasn't in its initial toolkit, it would just stall out or make something up.
Exactly that, or hallucinate a result. Even the more advanced ones, sometimes called deep research agents, they were often still limited, maybe 5, 10 tools max, web search, code interpreter, that kind of thing. DeepAgent aims higher tackling tasks that might need any tool from potentially thousands. Toolbench has 16,000 APIs. You just can't handle that with a fixed, predefined set. The old way doesn't scale.
Right. So DeepAgent flips this. Instead of separate steps, it's one continuous flow of reasoning. How does the main model, the large reasoning model or LRM, actually juggle this? How does it decide, moment by moment, okay, now I need to think internally versus now I search for a tool or time to make an API call?
The LRM basically generates everything in one go. Its actions are just specific text patterns that the system knows how to catch and interpret. There are 4 main types it can output anytime. A think for just internal reasoning, a search to query its tool library, a call to actually use a tool it found, and a fold to trigger that memory compression we mentioned.
Let's zoom in on a search. That tool discovery part seems crucial, especially with potentially 16,000 APIs. How does it efficiently pick the best few tools when the agent decides it needs to search without just drowning the LRM in documentation?
Good question. They use dense retrieval. So when the agent generates a search query, let's call it the tour, the system doesn't look at the tools one by one. Instead, it uses an embedding model, ADO Ethidior, to represent both the query and all the tool descriptions, ADO BASI. It then calculates the similarity, usually cosine similarity, between the query embedding and all the tool description embeddings. It just pulls the top carry most similar ones. This embedding-based search is super fast and what really allows it to handle those huge open set scenarios.
Okay, retrieval finds the top candidates, but what then? API documentation can be really long and verbose. If you just dump that into the main LRM's context, wouldn't that cause its own problems, like information overload?
Yes, and that's where the auxiliary LOM comes in. It's like a dedicated helper model. Its job is specifically to process stuff in the background. So it takes that retrieved documentation, or maybe the raw output from a tool call, and cleans it up. It summarizes, pulls out the key bits, filters out the noise. What gets fed back to the main LRM is concise and actually useful, keeping the main reasoning process focused and not swamped by irrelevant details.
Having that dedicated summarizer makes a lot of sense for keeping the main model on track. Okay, let's switch to memory. Managing context over long tasks is, it's critical. This autonomous memory folding in DeepAgent is pretty unique. How does the agent figure out that folding is the right move instead of just plowing ahead with its current line of thought?
So the agent itself learns to trigger this. It generates a special token, fold thought. The policy model, through the RL training, learns when this is strategically useful. Maybe after finishing a sub-goal, or more interestingly, when it figures out, hey, this path isn't working, or I seem to be stuck. It's sort of a learned mechanism for like stepping back and reconsidering its strategy, metacognition almost.
And when it triggers that, the memory gets compressed into those three parts: episodic, working, tool memory. You mentioned it uses a specific agent-usable JSON data schema. Why JSON? Doesn't that risk simplifying things too much, maybe losing some nuance compared to just letting an LLM summarize naturally?
That's a really sharp question. It seems counterintuitive, maybe, but the structure is actually key. The problem with unstructured summaries from LLMs is, well, they can hallucinate, right? Or mix up context, corrupt the information. By forcing the output into a strict JSON schema, they ensure a few things. One, it's machine readable, stable for the LLM. Two, it adheres to a specific model for each memory type, what kind of information goes where. And most importantly, it seems to really cut down on those LLM errors, making the compressed memory something the agent can reliably trust.
Okay, let's pivot to the training side. Agentic RL, as we said, it's tough. Two big huddles: cost and stability, and the sparse reward problem. ToolPO tackles both. Let's start with stability and cost. How on earth do they train this thing effectively with potentially 16,000 tools involved without breaking the bank or dealing with constant real-world API failures and delays?
Yeah, they sidestep that entire mess by using an LLM-based tool simulator. Essentially another LLM, maybe the auxiliary LLM or one like this, is trained to pretend to be thousands of different APIs. It mimics their responses. This gives them a training environment that's stable, fast, cheap, and completely predictable. You need tons of consistent interactions for RL to work well, and hitting real APIs during training is just, well, it's a nightmare. This simulation is critical.
Makes sense, a controlled environment. Now, what about the sparse reward issue? In a long task, the agent might do something really smart at step 5, like call the perfect tool, but then mess up later and fail the overall task at step 10. How does ToolPO make sure that crucial good step at step 5 actually gets rewarded and reinforced?
Right, that's the core of the credit assignment problem. ToolPO uses a clever trick based on PPO with two different reward signals. First, there's the standard task success advantage. That's the overall reward for succeeding or failing at the end, and it gets applied, in a sense, to all the tokens generated throughout the task.
Okay, standard enough. What's the second part? The innovative bit.
That's the action level advantage. This reward zooms in on the quality of specific actions along the way. It has a couple of components. There's a score that actually encourages doing memory folding efficiently when needed. And then there's a binary reward, CO call, which is basically just +1 if a tool call was correct and relevant at that point, 0 otherwise.
Okay, walk me through that failed example again. Correct tool call at step 3, task fails at step 7. How does ToolPO isolate the reward for just step 3?
So think about the whole sequence of tokens the agent generated. ToolPO uses a mask, my ITMIC. This mask basically says, only pay attention to these specific tokens right here. And it applies the action reward only to the tokens that actually made up the call command for the correct tool at step 3, or the tokens for an A-fold action. It ignores all the reasoning tokens before and after that specific action when calculating this action level reward. It's like surgically applying credit just to the decision point itself. This gives a much cleaner, more direct learning signal for how to use tools well, even if the overall outcome wasn't perfect yet.
So the mask is the key technical detail there. It lets them reward the action without rewarding unrelated thought tokens around it. Okay, bringing it all together then, this unified architecture, the smart memory, the fancy RL training, what did it actually buy them in terms of performance? Where were the results most impressive, especially for someone trying to build practical agents?
Yeah, the gains were pretty clear, especially in two main areas. First, just general tool use on established benchmarks. On things like TMDB and Spotify tasks, the DeepAgent 32B model trained with RL really pulled ahead of other 32B parameter models. We're talking scores like 89% and 75% compared to maybe 55% and 52% for strong baselines. That's a pretty significant jump, like a 20-point improvement roughly.
But the real acid test was scalability, right? Handling massive tool sets.
Absolutely, and that's where it really stood out, the open set scalability. On Toolbench, with its massive 16,000 plus tools, DeepAgent 32BRL got a 64% success rate. The best competing method, which used a more traditional workflow approach, only managed 54%. That's a solid 10-point gap, and it strongly suggests that weaving tool discovery into the reasoning process itself is just fundamentally more robust than trying to figure out all the tools you might need up front.
And that memory folding mechanism, it wasn't just theoretical. It actually helped in practice on complex tasks.
Totally. They tested it on really long horizon complex stuff like the GAIA benchmark, that's for general AI assistance, and also ALF World, which involves embodied AI tasks. The memory folding was crucial there. They did ablation studies, basically turning off the folding mechanism. And on GAIA, the success rate dropped noticeably from about 53% down to around 45%. Being able to autonomously pause, reflect, and clean up the context buffer is clearly vital when tasks get long and complicated.
And one last point they showed, this wasn't just about one specific model size. The architecture itself seemed to generalize when they swapped in much larger mixture of experts models like Qwen 3 235B. What's the implication there for people thinking about deployment?
It suggests the architectural advantage is real and somewhat independent of the base model size. The performance difference between DeepAgent and the older methods actually got bigger on some tasks, like WebShop, when they allowed more actions. For a practitioner, this implies that if you're building an agent for something complex, like automating a long e-commerce workflow, DeepAgent's approach might be less prone to hitting a wall where it just takes lots of inefficient steps. Each step seems to be more strategically valuable, especially as tasks get longer.
So wrapping up, DeepAgent really presents this end-to-end framework tackling the rigidity and scaling problems of earlier LLM agents. It brings reasoning and tool use together seamlessly, uses that clever RL training, and has this autonomous structured memory system.
Yeah, I think the big takeaway here is that making agents smarter isn't just about scaling up the base LLM. The actual architecture that manages how the agent thinks, acts, and remembers is profoundly important. And honestly, the success they showed with forcing memory into structured, machine-friendly JSON instead of just relying on free-form text summaries, that's a huge practical insight for anyone designing these systems. It combats drift and hallucination.
That definitely points towards future directions. And considering how well this architecture seemed to work across different model sizes, it raises a really interesting question for you, the listener, especially if you're in research. If DeepAgent showed the power of fine-grained RL for rewarding tool usage, what's the next frontier in applying similar fine-grained RL, but maybe this time to optimize token generation within those massive MoE models? How can we better reward the most efficient or insightful reasoning pathways at the token level, really unlocking the strategic potential of scale for agentic AI? That's something worth chewing on for your next project.